Thank you, lady. All right. We brought this board from David. David was very kind to give it to us. Which is a blank board.
Well, sure it's blank.
Yeah, I am. You'll see in a minute. That's on the cover. Can you peel it off? Yeah. There you go. Yeah, we believe in big boards. So, anyway, welcome to the August meeting. And we're going to try something new. And that's basically a combination of using a whiteboard and Zoom and being able to, have a group and people that can't make it here. So we got sort of a hybrid meeting going on. Now, the question is, how do you keep this thing on there?
Let's see what.
Or you're going to have to put it on two chairs. Really. Yeah, I don't have the chairs. So. There it is. Well, you're responsible for keeping it there, right?
I'm responsible. What about gravity?
Gravity. Okay. Well, anyway, David Sortis, K1KK, is going to be talking to us about all kinds of antennas and hopefully answering your questions. And then we can have a meeting, brief meeting, and see what we want to, any business of the club. So with that, David Sortis, K1KK, go for it.
Okay, ready?
Ready.
Ready.
Okay, let's do a short recount of what happened last time we had using that little board over there. Okay, just so everybody comes up to speed. Last time we talked about the properties of a quarter wave line. The coaxial cable, it could be an open wire line too, but let's stick to the coaxial cable. And basically we were talking about the properties of the line that is a quarter wavelength. A quarter wavelength, electrically speaking, or 90 degrees, not a full quarter wavelength physically measuring it. The length of a quarter wavelength will be in meters, will be 75 divided by the frequency in megahertz times the velocity factor. Why the velocity factor? The transmission lines, when the waves is propagating inside them or by them, they don't go at the speed of light, which is represented on physics by the letter lowercase c, which is 300,000 kilometers per second. Okay. So on the coaxial cable, there's a velocity factor, and a typical one, for example, this cable that I have here, which is an RG213, the velocity factor is 0.66, which means that the waves inside the coaxial cable are traveling at 66% the full velocity of the light in free space or in the vacuum out there in the outer space. So this is the formula. We said also that whatever happens on this side, let's say if I got an open here, an open circuit, here will be the opposite, will be a short circuit. Okay. Also that when we have two of these lengths together, in other words, we have here lambda quarters. Lambda is the wavelength. In total, we have here half wavelength. Whatever happens here, any condition that you see here, you will see it also on the other side. It will repeat itself. Why? Well, think about it. If I have let's say I have a short here, then quarter wave further into the line, I will see an open. And if I go again quarter wave, I'm gonna see the opposite of what is here. Quarter wave away will be again a short. So this is closed. Other properties we talk about it was using it as a transmission line transformer. Let's say that I have here an impedance which is Z1 and another impedance here on the other end that is Z2, and I need to match them. Well, I can put a transmission line in between these two that is a quarter wavelength long, and the impedance that I need to have here is equal to the square root of the product of these two. So Z1 and Z2 multiplied square root, that's also called the geometric mean of the two numbers, Z1 and Z2, and I will get the impedance that I need on this transmission line to match Z1 and Z2, okay? For example, let's say that I have my radio is 50 ohms on this side, but I have an antenna here that is bringing it up to this point 100 ohms, okay? So I got that Z1 is 50 ohms and Z2 is 100 ohms. So if I want to put a quarter wave transmission line here to match these two, it will be Z0 is equal to Z1, 50 ohms, times Z2, which is 100 ohms. This gives me square root of 5,000, which is pretty close to 70 something ohms, like 17.7. This is if you look at it, if this was 4,900, the square root of 4,900 is 7. So 5,000, the square root of 5,000 is pretty close to 70 ohms. Meaning if I put a line, a transmission line, which is with a characteristic impedance of 70 ohms, at this point, I will have a match between these two mismatches, okay? One property that we can use for this is when we do phasing antennas. Let's say that I have an antenna 1 that has 50 ohms. I come here with a certain length of 50 ohm cable, and I have a second antenna which is the same. They are like twins. They don't need to be twins, but in this case, let's assume they are twins. So I can put here at this point, which is 50 ohms, I can put a 70 ohm line. Needs to be a quarter wave. So let me put this a little bit longer, more space. So I got 50 ohms here. I got 50 ohms here. Then I put a transmission line, which is quarter wave. And this one too is quarter wave. And they are both 70 ohms. So what's going to happen? If I have 50 ohms here and I put a line that is 70 ohms and a quarter wave, it's gonna turn into 100. So I'm gonna have 100 ohms here and 100 ohms here. I can put here a coaxial T and come down here to the transmission line that is going to the radio. If I have two resistances that are 100 ohms and 100 ohms in parallel, that goes down to 50 ohms. So that's a way to match these two lines. What is the problem? If I get my antennas and without any transformation here with this quarter wave line, I connect it right here with just a T. Every cable here is 50 ohms. I'm gonna have 50 ohms and 50 ohms in parallel. That will give me 25 ohms. And 25 ohms against 50 ohms is the SWR is going to be 2 to 1. Okay? A mismatch. Okay. that was what we talked last time, and a little bit of the application of this property of the quarter wave line with a coaxial cable. Regarding the half wave line, in theory, we could use, let's say that we need to reach an antenna to connect an antenna to a transmitter, and I don't have a 50 ohm cable. I can use any other value of this, of half wave length of transmission line. It could be 70 ohms. It could be 37.5 ohms. Any value. If I put it that the length at the frequency I'm going to work at is half wave in electrical length, let's say that I have an antenna here. I have my antenna here, and it's 50 ohms at this point. Well, this line could be any value, 70, 35, 90 ohms. But if it's half wavelength, whatever I have here is going to be repeated here. So my radio or whatever system I have here is going to see 50 ohms. So it's not going to see the SWR. Kavit. Inside the line, the SWR will be there. So if I put here a 70 ohm line, and it's half wavelength, yeah. If I have 50 ohms here, that's what I'm going to see here. But the SWR within the cable is going to be there. In this case, the SWR is going to be 70 divided by 50. So I'm going to have a 1.4 SWR. Okay. Sometimes that might come in handy if I don't have any other line and I can cut the cable. I also explained that there's a way to do this. How do you cut a quarter wave? Sometimes it can be good enough just to calculate with the formula. Let's say this RG 213, the velocity factor is 0.66. So to calculate a full wavelength will be 300 divided by the frequency in megahertz. This is in meters. What I'm obtaining here is meters. For feet, I think it's 968, something like that.
So
936. I don't remember now, but anyway, we're gonna work here in meters. So this is for a full wavelength. A quarter wavelength will be 300 divided by 4. Okay, that and the frequency in megahertz. In other words, I got 75 times divided by the frequency in megahertz times the velocity factor. So let's say I want to do a line that is a quarter wave for 14 megahertz, more or less. Then I would do a quarter wave for 14 megahertz, let's say 14.2 megahertz, will be 75 divided by 14.2 megahertz times the velocity factor of the RG213, which is 0.66. This, somebody has a calculator there and can do the math. This should be pretty close to about 3.3 meters, something like 11 feet, more or less, 10, 11 feet, more or less. How much?
3.48 meters.
Okay, 3.48 meters. That's including the velocity factor. Okay, 3.48 meters. So I can cut that and maybe just use it like that. But there's a pretty simple way to do this, and we only need to have a T connector, a dummy load, a 50 ohm dummy load, and an SWR meter, or it could be your own radio if it has a way to measure the SWR. So let's try. Let me show you. This is already cut, and this one is for 40 meters. You can see there that it says 40 meters, 0.25 S, meaning that it's a short, and well, the only HK1A. Me. Then, if I do this connection the way it is, which is I have my T connector here. Here I put the dummy load, 50 ohms. And here I connect the line that I'm trimming, that I'm cutting to make it 90 degrees or 1/4 wavelength at the frequency that I am intending to. And then here I can connect an antenna analyzer that's going to measure the SWR, or I can connect my radio. It doesn't matter. Okay. And when this line is a quarter wave, it needs to be shorted here. So I connect the center conductor to the outer conductor. And if I see a short here, there's a short here that I'm connecting. Remember, if there's a short here on a quarter wave line, I'm gonna see on the other side an open. It's just like nothing is connected to this side of the tip. In other words, the SWR should measure pretty close to 1:1. And if I disconnect and connect back this line, there won't be any difference. I still should have the 1:1 SWR. So here you can see there's the dummy load, the quarter wave stop that is shorted at the end.
David, don't give me your bag.
Okay. It's shorted at the end. And I'm reading now 1.02 SWR.
Yep. Got it.
Okay. So you can try, please take, hold here. If you disconnect this here, it doesn't change much. No. It still keeps the 1.03. It's pretty simple to do. You only need to calculate with the formula, cut it a few inches longer, and then start trimming. Yeah. Now, another thing.
Well, here, hang on a minute.
Uh-huh.
All right, change the frequency so it does show, so you can show them how sharp and odd you.
Okay, let's do a graph. Better yet. It's plotting it there. You can see that the frequency, which is 7.1, right? It's
Plus or minus 2
the
megahertz.
minimum. Maybe you can show it.
Yeah.
Mm-hmm.
You'll see that.
No.
Show me the display, will you? Just aim it towards me. Okay, let me see if I can get it. All right. Then. Yeah, I see it. Okay, good.
Okay.
Good. Thank you.
Then the depth and the sharpness of this curve that you see here will be like deeper, will be sharper if the quality of the coaxial cable you are using is better. So the better it is, it will be narrow, the curve will be narrower and higher attenuation at the frequencies that are away from the design frequency for this stuff. Okay. Then the other thing is that one thing I mentioned before was that when you are doing this process, you have to, measure, put the short, and then cut if it's necessary to cut, and then establish the short again, and that is time consuming. One way that you can do is, instead of using a short here, you can use an open. Instead of being a short circuit here, you can put an open. And what's going to happen? So you need to see an open on this side. So to see an open, in order to see an open from the opposite side in here, you need, instead of a quarter wave, you need half wave. So whatever you have here is going to be repeated here. So if you are cutting a cable, let's say that is for 7.1 megahertz, you're going to cut it for a quarter wave at 7.1 megahertz. But 7.1, a quarter wavelength on 7.1 megahertz at twice the frequency, 14.2 megahertz, it will be a half wave. So you can do that without having to do the short on this end using a half wave. This cable, I'm not sure. Let's measure it with precision, like my friend Peter likes. Yes.
Oh, sorry.
Doctor Millimetro.
Millimetro, huh?
So in his man cave, I measured like 33 feet, and the error was 4 inches. Okay.
Hey,
So
you tell your women that's 8 inches.
So this is like more or less, I would say, it's pretty close to 3.3, 3.4 meters. Okay, this is about 1.6 meters. So we have about 320 twice, and then 20 centimeters. It's about 340, 3.4 meters. So this will be pretty close to a quarter wave on 14.2 megahertz. So on which frequency this will be close to half wave? Twice the frequency. So at 14.2 times 2 is 28.4. Let's try it out and see what happens. Remember, this is not shorted at the far end. So this is open. So I'm looking now to measure not a quarter wave, but a half wave at twice the frequency. So I'm going to program it here.
So basically it is shorted, but just because of the length of the wire.
It's a half wave. Well, it's a half wave on 28.4.
Yeah.
Or a quarter wave on 14.2. Same length.
So there it is. Now that is plus minus 1 megahertz, and the center frequency is 28.4. Okay.
Super.
Uh-huh.
Shut her in.
28.4. Yep. Okay. So you see that the minimum is on the center frequency at 28.4 megahertz. Okay. Now I can just I could put a short here. You short this end and go down to 14.2 megahertz, and it should be the same. Should give me a quarter wave length on 20 meters, or what we are measuring here, half wave on 10 meters. This is quite simple to do. And with this method, you can do any length, not only 90 degrees or a quarter wave. Okay, you can do any other type of line. Let's say 84 degrees, which is a little bit shorter than a quarter wave. You could do that instead of 90 degrees. Simply applying a little bit of proportion, inverse proportion. But you should try this maybe sometime. And this is useful, for example, to match a quad antenna, which has like 100 ohms. Match it with a 75 or 70 ohm line, 70 ohm transmission line. Match or get it closer between the quad impedance, closer to 50 ohms, and have a decent SWR. Okay.
Demonstrates why everybody should have an antenna.
Why you need one of them?
I mean, no kidding. They're getting fairly cheap, so antenna analyzer.
Yeah, I have one of these nano VNAs. So it's not only an antenna analyzer, it's just like a 2-port instrument like this one. But well, this one is sold at a resolution, north from $1,000. The other ones are like $100, $60, $70. They are not like precise maybe, or have the dynamic range that this one has, but this is pretty good enough for the ham activity. No problem at all. In the 50s, not very precise, huh? I have one. I have one at home. Yeah, it's very interesting with the little coupling coils or the noise bridge.
Yeah,
The noise bridge. Those were the things before, but now you can get a VNA that is about this size, goes up to 1.5 gigahertz for under $70. Yeah, and it's good enough, and you can connect it to the computer and have very nice graphs. Okay, that was about the recount, and I wanted to add the practice showing how it's done. You can see that it's pretty simple. You don't need to have much knowledge, and simple instruments, just like a dummy load and a coaxial T. Yes.
Question. If I'm putting out a monobander out there, do I want a half wavelength or a full wavelength for that frequency to feed it?
No, it shouldn't matter. Once you are matched, there's some myths about the magic length of the transmission line. But if your antenna is matched to 50 ohms, it shouldn't make a difference. And I could explain that, not today, with what happens with an impedance along a transmission line, a certain length of a transmission line with the Smith chart. But in the Smith chart, remember that if you are in the center of the Smith chart, you are looking at 50 ohms plus J0. So that's a perfect match. And if you are there, no matter how you rotate your line, you can count your line and move it here. If you're here, you're going to be circling around this point. So you're going to be on the same spot all the time. It shouldn't matter. Now, if you are in a mismatch out here, and then you put that to a certain lane of transmission line, then yeah, it's going to move and be somewhere else. But that's out of the scope of today's talk. Okay, so I'm going to talk a little bit about formulas. Please don't keep your window of understanding open. I'm just putting the formulas, and it's not necessary to understand them to get the message of what I'm talking about. But there are some people that can handle the formulas and the numbers, and it's good for them to have. And the ones who don't, learn it. It's unavoidable. There's going to be numbers here always. Okay. The decibel. Okay. We have seen decibel. This is the right way to write it. Okay. Not with capital D and lowercase b. or any other combination. This is the only one that is correct, okay? Why? Because we have the prefixes for the units, for the quantities, which are, deci, meaning 1/10, okay? Then we got centi, like centimeter, or centiliter for 100, and we have milli for 1,000, etc. And all these units are always written, and the abbreviation is with lowercase. So we got dB. And what happens with the B? It needs to be capital because this unit owes its name to a name of a person. So things like Farad, that comes from Faraday, is with uppercase. Same for the bell, obvious. Who was that? Alexander Graham Bell. Okay.
He stole it, he got away with it.
Yeah.
You're thinking of Edison.
I'm sure that. So there are other units. I think that the only one that is written with uppercase and is not, doesn't correspond is the liter. Liter, 1,000 cubic centimeters. That's the only one. The rest, if they belong to the name of a person, like the coulomb, the unit of charge, is with capital. So let's go back to the dB. You have heard about dB, dBd, dBi, dBm. What else? Okay, that's about it. There's also not much use, but there's also dB over watts, but we don't care about that one. Okay, the dB is an eight-dimensional unit, meaning that it has no units. It's a ratio, it's the expression of a ratio. And basically is, if I have power 1 and power 2, if I have power 1 and power 2, I apply the logarithm to this ratio and multiply by 10, and I get the gain in dB, in decibels. Okay? The opposite formula for a radio will be power 1 divided by power 2, and then 10 to the power of the gain divided by 10. Okay? So this is a way to have a gain in dBs and convert it into a factor or a ratio between two powers or two levels. There's another one for the voltage. When instead of having powers here, you have voltage. I don't use it much, but it's like this. Then instead, I have B1, B2, and B1 in a ratio form here. But this is the one that I use the most. And the people that work in the radio frequency world or the electronics world, most of them, they have, from memory, they at least know the first 10 ratios. I'm gonna just write it here from the top of my head. Let's say I have dBs here, gain, 1 dB, 2 dBs, 3, 4, 5, 6, 7, 8, 9, 10. And then the factor, that could be P2 divided by P1, because the ratio of powers will be around 1.26. And then the second one will be 2.57 2.54, more or less. If you multiply 126, well, it's not 126, it's like 126.89, etc. If you square this value, you get this one. And if I multiply again this that corresponds to 2 decibels by 1.2, then I will get pretty close to 2. Okay, that's so 3 dBs is a power factor of 2, or it could be the opposite. If I am taking 3 dBs off, it's gonna be, instead of multiplying by 2, I'm gonna be dividing by 2. Okay, so we have here, to do it quickly, 2.5, 3, 4, 5. This is like 6.3. This is pretty close to 8. I think it's something like 7.94. You can do it. You know, you can take the 8 and 8 to the 10, or in other words, 10 to the 0.8 power should be this. Okay. Then we got the 10, which is 10 to the 10 divided by 10 is 10 to the 1. So it's a factor of 10. Okay. If you know this, you can calculate the power factor of any other value of dBs. For example, let's say that I have an antenna that has a gain of 25 dBs. Okay. So this is 20 plus 5. 20 is a power factor of 10 to the power of 20 divided by 10. So in other words, 10 squared, which is 100. So I know that this part gives me 100. And from the table, the number 5 dBs is 3 more. So 25 dBs is a power factor of 300. Okay. I always remember when my dad told me, I don't see that you do the logarithm tables. You know, it's easy to multiply with that. And, you know, I never even bothered to learn it. But once I learned this, I realized that the mechanism, how it works, and how it's easy to multiply and do other operations with big numbers, making them smaller using the logarithms. Okay? Well, this is the same principle. It applies to it. So now let's go to DVI and DVD. There's a theoretical antenna that is called the isotropic radiator. It has no dimension. You know, we cannot even in theory imagine it like a very short dipole. That would be an approximation. It's basically a point in the space that it radiates. And it's an antenna that is not real. There's a mathematical definition for it, but it's used as a reference. In today's market, we use the isotropic reference, and then we use the dipole reference. So when we are talking about isotropic, and you see the gain on a magazine, on an advertising about antennas, if you see, and don't trust that no matter what, if you see, for example, that an antenna has 4 dBi, it means that this antenna, it has 4 dBs over the isotropic theoretical antenna, which is a dot, a point, and its radiation pattern is just like a sphere that has the radius, equal radius in all directions.
Can I hold your? Nope. It's a Nikon. Okay, I think we're back up. Okay, good enough.
Good?
Thank you.
Okay. So it's very important when somebody's telling you about the gain of an antenna or an amplifier or anything, which are they talking about? You know, is dBi or is dBd? If they say, for example, 4 dBd, it means decibels refer to a dipole antenna, which is something standard that everybody knows what the gain is. Now, the isotropic antenna has 0 dBi. What that means that an isotropic antenna is not going to have gain over itself. It's going to be 0 dB because it's the same. Remember, you say 0, you got 0 that's can be, well, remember, 10 to the 0 divided by 10 is 10 to the 0, which is 1. So the factor is 1. So I forgot here. 0 dB, factor is 1. And the dipole has 2.15 dBi. So the dipole has a gain of a little bit over 2 dB over an isotropic antenna. And if you apply this formula, it will give you that the power factor of a dipole over an isotropic antenna is 1.64. In other words, let's say that I am transmitting with a theoretical antenna and isotropic antenna, and I have also a transmitter with 1 watt into a dipole. To put the same amount of signal in certain distance, I'm going to need 1.64 watts times the power that I'm using with a dipole to produce the same with a lower gain antenna like the isotropic antenna. In other words, if I transmit with 1 watt with a dipole on the same frequency, I'm going to need 1.64 watts to acquire or to produce the same signal at a given receiver with the isotropic antenna. Okay. And well, the other one you don't see much, but this one dBm is used a lot on microwave and in general in radio frequency engineering. And it's dBm means decibels over a milliwatt. It's expressed like dB and lowercase m, dBm. So if I have, let's say, no, my microwave radio is transmitting with 30 dBm. That means that the radio has a power of 30 dBs over 1 milliwatt. And 30 dBs, 10 to the 30 divided by 10 is equal to 10 to the 3, which is 1,000. In other words, 30 dBm is equal to 1 watt or 1,000 milliwatts or 30 dBs over a milliwatt. Okay. Okay, that is all about the dBs and the references. Any question until now? No? Okay.
Clear as mud, as they say. There will not be a test. Right.
Oh.
Anybody who wants to review it, we'll get it up on, there'll be a link from our W4AMC page to Vimeo, so you can see it again if you want. Sometimes getting it a couple times like that helps you get a hold of it.
Oh, making, questions too.
Yeah. Mm-hmm. Think of that.
Okay, let's talk about polarization. What is polarization? Ego te absolvo. Ay, nomini patria, okay.
I know you're gonna.
Okay, well, you know it. Polarization, there are several types of polarization. We have linear. That's the one that we are more used to. Okay. We got also elliptical. And we have also circular. These two are pretty close together. It's only about eccentricity. One is not a perfect circle, and you get more. Like your antennas on the roof of your office, they are elliptical. Oh, I forgot to take a picture. We call it circular, but it's elliptical. I send you a link.
You want to see that link?
Yeah, let's show that link.
Okay.
So let's say that this is my vector of propagation. My waves are propagating in this direction. They are being emitted from here. So this is an electromagnetic wave. So it has two components, one electric and one magnetic. Okay. Let's say that this is the electric one.
Okay. You want me to do that video now?
You have it there? Okay.
Yeah.
Okay, 1 second. And then we got the other one that is 90 degrees apart and is the magnetic one. Okay. So it's not like if we could, use some magic glasses and look at this and we're going to see the wave like that. It doesn't happen. This is just a representation that shows you at a given time and position in space what is the sign, the polarity of the field, negative, positive, or neutral at that point. Okay. So this is just a representation. It's not that if we could see the wave, we're going to see him like this, like we see him on an oscilloscope. Okay. So the thing is that at a given moment, this is a vector that shows what is the amplitude of the electric field. Okay. And there's another vector that is showing me what is the amplitude of the magnetic field of the electromagnetic wave, the EM wave, okay? And there's a resultant to this. If I add these two vectors, I'm going to have a vector that is the addition, the vectorial addition of this amplitude and this other vector that is showing me the magnetic amplitude. And we're going to have what is the resultant vector and its magnitude. Okay. Play it again, Sam.
Play it again, Sam. Let's see if I can do this without blowing things up. Okay, now here we go. Now, I don't know that the audio is on.
No, there's no audio. I checked
Okay,
it out,
here you go.
there was no audio.
Okay, so now you can see it there.
Okay. Basically, the vectors are changing sign, and moving across the zero axis or the axis of propagation. Okay, pause it there 1 moment to make an acceleration here. I was talking here about one wave with electrical and magnetic field, okay? This case is a combination of two linear waves. I got two emitters, two transmitters, and both are producing linear waves. One is going horizontal and the other one is coming vertical, okay? And if you see at the beginning of the video, try it again at the beginning.
Play it again, Sam.
Yeah, the two waves, they begin at the center. They are at zero. Both of them are zero, and then they start undulating. You see? They come from the same point. So what you get is, you see the linear polarization resultant is the green one, the green vector. That is the addition of the two different linear waves, one which is horizontal and the other is vertically polarized. And if you see this one, green, is not changing directions. It's always like, you know, one is coming like this, the other one is like this, and then this one is the resultant that is 45 degrees. It's just doing this, yeah? Moving on the same, on a 45-degree plane. Keep on going.
Okay.
Now look what happens. Stop it there. Okay. Now, this one has been moved a quarter wave before. You know, remember that this point, well, now it's on the back, but it's an equivalent point. This point was at the same point here, zero, with the other one. But now this wave has been shifted backwards. So we are like delaying it, you know, like retaining it, and we are not letting it start the race against the other wave, the blue one, at the same time. We're holding it there and we let the blue run a little bit. A quarter wave of advantage we're giving it, you know? Okay, running. Now you can see that the vectors, they are not like having the same amplitude in their own directions all the time. And look what happens. Okay? That is circular, and looking for the point of origin is moving this way. So this is right-hand circular polarization, clockwise. Okay? The only thing done there is you held the emission of one of the waves, quarter wave. You say, hey, hold it here, don't move. Let the other one run a little bit, and then, okay, now you can move. And look at the difference. You went from having a combination of horizontal and vertical polarization, like in this angle, to have something that is moving circularly. That is circular polarization. Then, going back to the antennas thing, now that we know that, there are several ways to achieve circular polarization or elliptical polarization, which is pretty close to circular polarization. Okay? One method is having jaggis that are put on the same boom. One set of elements is going to be horizontal or any other direction. They don't need to be horizontal, and the other one is just going to be 90 degrees away. Okay? They can be like this, or like this, or like this, or like this, or like this. It's going to be the same effect. It doesn't matter. They don't need to be like parallel to the ground and the other one parallel to the vertical. So I say that this is my reflector. There are two ways of doing this. And then here is my feed point of one of the horizontal element antennas. And then I can have a feed point for the vertical one. So this is vertical and this is horizontal. Remember, I'm just calling them vertical, horizontal. They are just 90 degrees apart, and it doesn't matter in which orientation they are, as long as they are 90 degrees. Okay? So I have my elements here and the common boom to the antennas. Then if they are physically on the same distance to the target, meaning that relative to the target, which is here, my antennas, both the vertical and the horizontal, they have the same distance, then how can I do to put this, that one is a quarter wave behind the other, just to get the effect that we got there on the video, that it became circular. Because if we just transmit like this, you know, we have the transmitter here, and we connect, there's a T, goes to this antenna, goes to this antenna. These T's, these lengths are the same. I'm not achieving the circular polarization. I'm just getting that combination that showed like a diagonal there on the green vector. It was just oscillating, but in this plane, it was not moving circularly, okay? So the way to do this is pretty simple. I can make this length of cable L1, and this one is going to be L1 plus a quarter wave more. So if this one is a little bit longer, it's L1, this one will be L1 plus quarter wave more, then I got my delay there. And it will produce circular polarization, right hand or left hand. I don't know now which one. Okay. And sometimes I may need to switch the polarization. So somehow I may introduce, you know, take this quarter wave line, and instead of having it here, there's a way to do it by switching the antenna. I can put it on the other side. Okay. Or I can just have, you know, a way to insert some extra length of line that will get me that difference of a quarter wave. The other way to do this is simply I build my antennas, and if this is the reflector of the vertical portion, the reflector of the horizontal portion is going to be here. This is vertical reflector, this is horizontal reflector. And then the distance here is going to be a quarter wave. So basically what I do is I get the antennas and just build them that they have a difference of a quarter wave between the analog elements of the antenna. That's another way to get it. Okay, that's a way to get circular polarization.
What's the advantage of that?
Of what?
Circular polarization.
For example, when you are working satellites, you don't know. Many of them, they have linear polarization antenna. But because the satellite is rotating, it's tumbling up there, you don't know, you know, that that linear polarization, how it's going to get to you. So with the circular polarization, you're going to get any linear in any angle that comes to you. Okay? There's more to it, but basically it's that you can have everything. Then one thing is that if you are a circular polarization receiver and a wave that is vertical or, you know, linear polarization, it doesn't matter in which orientation it comes, you will receive it anyway, but you are losing 3 dBs. But 3 dBs is better than not having a circular polarization and you are like this polarization and the signal you're receiving comes like this. The difference can be 30 dBs, 20, 30 dBs. So that's 100-fold, a 1,000-fold. You're not going to hear it probably.
Is that also why you get that fading, that periodic fading on those signals? Because it's rotating and you may have a linear polarization.
There could be that effect, but the fading is mostly when you have like reflections and then you get like multipath from the transmitter to the other. So, you know, you send a signal directly to you, but then a little bit goes and bounces somewhere and then goes back to your direction and they get to you out of phase. And that may cause the fading, okay? Another way to get a circular polarization is with one antenna that is called the helix. It's basically a reflector, and then you have something that is like a helix. Looks like a spring. General dimensions of this thing are like 0.3 lambda here. So if this is 0.3 lambda, every turn, let's say you start here and you do the first turn and end here, is more or less one wavelength. Okay? this antenna is very forgiving on the dimensions. You can do it, not be precise, and it will, you will be on the spot. The antenna has like a 30% beam width. Okay, that's a lot. So we're talking that if I design one antenna of this for, let's say, 1,000 megahertz, it's gonna have a beam width of 300 megahertz. That's a lot. These antennas are normally used in high frequencies. Why? Well, 0.3 lambda. If we're gonna use it on 2 meters, that helix will have over 2 feet in diameter. Long maybe from here to the wall, depending on the number of turns. There are curves to design these that, depending on the amount of turns, there's an optimal diameter for this, and also the step or the distance between one and the next turn. There are several things there, and depending, you can easily know if you, let's say this is the back of the antenna. If you wind that coil like this, it's gonna be right-hand polarization, right-hand circular polarization, or the other way will be left-hand circular polarization. Yes.
David, is there a gain loss was that included?
Well, depends on how many turns you do on, or how many elements you do.
I mean, if they're weak.
I know that that one like this, for example, of let's say 12, 13 turns, it may be 12 to 15 dBi of gain. Yeah, it depends.
That's a linear reflector in the left side.
No, let me do like a 3D representation. Normally you have like a reflector, like some spokes here to hold it, and then you get the, and this is the axial mode. That's the direction of transmission. One thing that happens with these antennas, they can be used to be put at the focus or the center of radiation of a parabolic dish. Okay, so we have a parabolic dish like this, and then here is the focus. What happens here? Every wave, every front wave that is coming here like parallel lines, they are gonna cross this point here, which is the mouth of the dish, and get here, hit the reflector, and go there. Again, cross this point, hit here, and go to the center. No matter where, the distance, if you add this distance and this distance, is gonna be the same, like this distance added to this distance. So as soon as the wave crosses the mouth of the dish, they are gonna be covering the same distance to reach the focus of the parabola, which means that everything is gonna get there at the same time. In other words, in phase. Okay. Then you can put a short helix here. There are some dimensions or requirements that you need for whichever antenna you use at this point. And one thing happens. If I have this, let's say I build this helix like this, pointing to the dish, meaning right-hand circular polarization, looking for the back, from the back of the antenna, from here, I look there, and then I see it this way, clockwise. Okay, that is right-hand circular polarization. What? Circular polarization, right-hand. But this is gonna transmit, and then transmit in this direction, and then go out. Okay? What happens to my right-hand circular polarization? it has bounced from some place. It turns the other way. So I'm emitting with a right-hand circular polarization helix, but as soon as it bounces here, it's gonna go the other way. Imagine yourself, seeing that spring coming against a wall and then coming back. It's gonna just invert the sense the other way. It came hitting the reflector right hand, and it's going out of the reflector left hand. Okay? That same phenomenon happens when you are doing EME, moon bounce. When you are bouncing your signals of the moon, if you hit the moon with right hand polarization, circular polarization, the waves are going to come inverted the other way. Apart from other things that may happen that are not on the scope of this talk today. That happens too. Okay? One last thing on the parabolic. The two main designs of the parabolic, the parameters are the diameter of the dish, which capital D, because there's another D, which is the depth, meaning the distance from the plane that contains the mouth to the bottom center of the parabolic reflector. That's D lowercase. And then the other one is F. And an important parameter of design is F divided by D, meaning the focal distance, which is where my focus is, to the center of the dish, and the ratio that is between F and the diameter of the dish. Okay? That's a very important one. And that dimension, that ratio here, dictates which is your angle. The angle that is subtended from the focus to this ring, the edges, the outer ring. This is important because the practice says, the theory says that you need to have something here to have the dish, the reflector, properly illuminated. So that is that you have to put an antenna here such that has a pattern that the gain here, of course, in the center is going to be the maximum, but here should be around 10 dBs less. So whatever you get here, your edge should be receiving from this antenna, should be receiving 10 dBs less. That's the optimal illumination for a parabolic antenna. And that's it.
Cool.
Questions?
Answers.
No, I'd like to say you did a really good job with it.
Thank you.
You're a much better artist than I am.
On the moon bounce, you need different antennas,
Experience.
orientation, one side, right, the other left hand.
Yes, depending on the band, I know that there's a convention that you transmit with right hand and you receive with left hand.
Okay.
So you may see sometimes, like these systems that they have the helix antennas, and you see two identical, but the only difference is that they are like mirror-like. One is left hand and the other is right hand. There's conventions for this. And I was reading about it, and I know that you need, for example, for 23 centimeters, 1300 megahertz, you need about a dish that is a minimum of 10 feet in diameter. And the same dish can work on the next higher band, which is 2.4 gigahertz. But then because it's bigger in wavelength, in wavelength, then it gets narrower. So you are talking about maybe like 3 or 4 degrees between the half power points, 3 or 4 degrees. So you gotta aim that very precisely. Mm-hmm. That's it. Anything else? Questions? No?
Well,